bigger than that.
What?
Way bigger.
All right, so okay. Real quick, because this is still something that you're struggling with a little bit. Appropriate property. So for electrical fields, what is that appropriate property that an object has to have before it will feel it? Charge. Good, getting better. Charge. And so what does charge mean? Not like it's full strength, your battery's charged up on your phone. Nye?
Unequal amounts of electrons and protons.
Very nice. Unequal protons and neutrons. Even if they're off by one, that's a charge. Obviously, the more that number is off, the more charge something has. Yes? Did I say neutrons? Dang it, thank you. Protons and electrons. Sorry, I was going with the nucleus there for a minute. Yes, protons and electrons. Thank you. So you could even just be off by that one, or you could be off, they could be off by hundreds or millions, right? Lots and lots of differences, but the more they're off, the more charge an object's gonna have. Then what is the appropriate property for magnetism? For a magnetic field to have an influence on something, what does the object have to have? What does it have to be? It has to be magnetic, right? Has to have the properties of those electron domains being able to all line up. And so not a lot of things actually have that, right? Iron, nickel, and cobalt naturally have that. And so those are kind of our common ones. Yes?
Is there a way that we could artificially make that?
It's a good question. I mean, with the electromagnet, you can kind of cause it to happen, but it still has to be an object that has that capability. So like, can I turn plastic? No. You know what I mean? Like, there still has to be, even with an electric current, like it has to have something special. It has to have those double electrons in that, you know.
Could you artificially make those double electrons spinning?
They probably have, like in a lab, I imagine they could probably synthesize or create that. Is it something that we could just do to like any random object? No. Right, that is a characteristic that is unique, and so it's not something that you can just automatically create or cause something to do. So, takes us to our third appropriate property for gravitational fields. What is necessary? Because we know that gravity, like there's gravitational forces and fields between everything, but for us to experience it, what does something have to have before, like, we actually can notice the effects? It has to be extremely massive, right? It has to have a lot of mass to it, right? So that's the appropriate property. All right, so slide 24. So we've said every object is going to exert a gravitational force on every other object that has mass. But these forces are hard to detect. And honestly, everything in our universe has mass except for the general category of energy. So like light energy, sound energy, thermal energy, which is heat. Those energies do not have mass, but everything else pretty much does. So even if we're talking a teensy tiny mass, like an air molecule, well, it still has mass, which is, it has a little bit of size and shape to it, and it has particles in it. Even if it's extremely small, where we're like, oh, that's nothing. Well, technically it's something, okay? All right, and so the appropriate property is extreme mass. So what are our examples of extreme mass? Like a tank, an elephant, those aren't even big enough. A mountain range, not big enough. Zach?
A black hole.
No. Macy? Planets, right? We're talking large, like planetary large.
What? So like
So like, even like stars, the moon,
the sun.
the sun,
That thing's
right, which
huge.
is a star. What?
Black holes have more mass than all those, though.
Okay, so we're not gonna get into black holes because there's a whole, we could spend like a whole chapter. If you're interested in it, there's a ton of information. You are more than welcome to like broaden your own horizons, but it gets us way off track because it is a very cool topic. And I agree, obviously anything in its area, it is attracting to it. But we are going to leave that alone for our discussion here, yes.
You know, scientists have found a white hole.
Really?
It does the complete opposite of a black hole. Instead of pulling stuff in, it repels it.
No way. I'm gonna have to look into that. Really? Is this like proven, documented, or like it's a theory?
See,
Really? Oh my, I need to look into that.
Does
That's
it
very
show
cool.
black
Okay,
every
you need
time?
to keep that bubblegum in your mouth, please, or else you can throw it away. Those are your choices. Okay. Alright, and so gravitational force is going to increase with the mass of the object. So the moon, our moon, is not nearly as massive as the Earth, which is why the moon is attracted to our Earth's gravitational field, and which is why it is orbiting around our Earth. It's closer to our planet, which is why it attracts to our Earth's gravitational field and not another planet. And then that's also why the moon revolves around the Earth and not the other way around. The Earth is more massive. Okay, so it always goes with the more massive object having the greater pull. Okay. And then just like our fart funk, the same thing is true here. The farther away you get from the massive object, the less intense that field becomes. Okay, so that's why as rockets blast out of Earth's atmosphere, very quickly they are no longer being pulled downward to the Earth and they start that floating kind of process. All right, they are no longer, it's not that Earth is not massive anymore and that it doesn't have this huge mass and it's not like its gravitational pull has been flipped off, but it is out of Earth's orbit and it is no longer being affected by Earth's gravitational pull. It's kind of like the fart funk, where if the source is this table and I walk away from the table, that fart funk gets less and less, right? Like I smell it less, as long as I have the appropriate property, right?
I think the
That's
phone's
fine.
ringing.
Yep, not mine. Thank you.
Hers has a
Yeah, I have a different
Weird
ringtone, because all of our phones ring was the same. And so it would be sometimes like, is that mine? Is that Miss Durchee's? Is that Miss Donahue's? Mr. Trainer? So I changed my ringtone. Okay. And the other thing is that the pull of gravity pulls towards the center of the object. Tucker, you with me?
Yeah.
Okay. All right. So I want to go back real quick. If you look here, these field lines, these arrows are showing the pull towards the center. So if an object is a sphere, like all our planets are, the strongest pull is at the center of the object. So dead center right here, which would be our inner core, which we'll talk about later this year. Right? If we have, let me get a normal pencil here. If you have an object that is not not a sphere, like a pencil, okay, to find the center of, sometimes we'll talk about the center of gravity or the center of an object's mass. Well, for a sphere it's easy, but for like a pencil, right, I can find it and find that balancing point. That is the center of gravity. Notice that it's off just a little bit because there is actually more mass at the eraser tip. Oops, so slippery, goodness. More mass at the eraser tip, so like I have to be a little bit off. It's not exactly in the middle of my pencil. So the center of gravity doesn't always have to be the actual middle of the object. You can see my finger's a little bit offset, and you guys can probably find that on yours as well. You get that more offset on a pencil or a pen that has like a clip and like the heavier tip. Normal pencils are pretty much right in the middle, but we're not saying that, you know, that's the center of that object's mass, when you can find that kind of tipping or balancing point, okay?
Uh-oh.
Okay, so, we kind of generically call any object that revolves around a planet a satellite, right? So, this could be, you know, a natural satellite like the moon. It could actually be like a satellite like you're probably thinking of, that, you know, is artificial that we put up into space. As long as it is close enough and it's within Earth's gravitational pull, it is going to revolve and rotate along with the Earth, okay? So our GPS signals, right? That is, you know, probably the most common one that you're thinking of, you know, for artificial satellites. Again, these can be natural ones like the moon also. But the Earth and all of these satellites have mass. Nobody's denying that. But obviously the Earth has a much greater mass. Therefore, the smaller massed object is going to respond to Earth's gravitational pull and not the other way around. So all you really have to do is ask yourself, which one it has more mass? And that's the one that's going to exert the greater force. And that's probably the force that you're going to be able to see the effect of. And it's gravity that's giving, is what keeps that satellite basically stuck to the Earth, right? Stuck with Earth's rotation and movement. And doesn't let it just go floating off into outer space. And that's why rockets are needed, like when NASA's launching spaceships, they have to have a rocket that will basically bust it out of Earth's atmosphere to get it away from Earth's gravitational pull. Okay, so they kind of hinted at this on the video. We inappropriately use weight and mass all the time. Like we might say weight when we mean mass, we might mean mass when we say weight. Okay, weight is the measure of gravity's pull on an object, and we have a song that you guys will probably really like, and it's kind of fitting because the World Series is starting today, and it's kind of a known baseball song, Sweet Caroline. We have a Mr. Edmonds version of it, but the way that I remember that weight is the one that's affected by gravity is they both have the letter G in it. Okay, so weight has a G, gravity has a G. Okay, and so weight is the one that's affected by gravity, because as you go, like, okay, here on Earth, gravity is going to be the same, right? The pull is the same no matter where you go. I could go to Utah, I could go to China, I could go to Africa, it's all the same. Japan, anywhere on the Earth, gravity is going to pull the same.
What if you're at the bottom of the Mariana Trench?
There's pressure of the ocean above you, right? But that's not more gravity. You're a little bit closer to the center of the Earth there, so possibly a little bit stronger, but the force you're feeling is more the pressure of the water on you, I would imagine. But if you go to a different planet, hypothetically, if they have different masses than the Earth, they're also going to have a different gravitational pull. And we'll look at that. We have a little lab that we're going to do that will kind of show this a little bit too. Okay? But the key is that weight is affected by gravity. So if you would go to a different planet where the gravity is different, then the object's weight will automatically be different because the gravity was different. All right? So the only time, let me think about this. So we know that mass is how much matter is making something up, right? So my mass is not changing drastically on a daily basis, right? You know, we might like be a little bit lighter in the morning and maybe be a little heavier in the afternoon based on like what we've eaten and drank for the day and stuff like that. But really, our mass is pretty consistent. Now, you guys, a lot of you are still growing, so a lot of you are actually adding mass to your body. Like over the summer, I come back and see like the freshmen that are now sophomores, and it's like, wow, like a lot of them grew like 4 or 5 inches, right? So obviously they have put mass on their body. Now, that's not super quick. It wasn't like literally overnight, right? So I have 2 examples where mass can change drastically. One's a good way, one's not a good way. So if somebody would happen to be in an accident maybe and like have to get something amputated, so like we have a freshman who's going around as Lieutenant Dan today for Halloween, if you've seen J.D. Albert, right? So hypothetically, Lieutenant Dan had his legs amputated. Well, the mass that was his body is now drastically been cut down, right? The amount of matter that made him up when he lost his legs from the knee down, that changed his mass instantly. When that surgery happened, when that explosion happened, and then they, you know what I mean, like boom, right? So that's not a good way for mass to change. The other one is if a woman has a baby, as soon as she's delivered the baby, first of all, the mass was there, now the mass is gone. I mean, just, right? And that's, you know, a pretty quick process. The baby's there, then the baby's not. Okay? We're not getting into any details besides that. Yes.
It's not quick, it takes 9 months.
So,
She's talking about when you're
when you actually deliver the baby.
She's
So,
talking
one minute
and
the
then-
baby's in you, and even if labor lasts for 24 hours, right, there's a point where the baby's inside, and then there's a point where the baby is not, right? So, like, think of a C-section, okay? So, baby's there, baby's out. So, the mass of the mother has changed drastically. Those are the only 2 examples that I can think of. I've had other people, like, try to, like, come up with things, but it's still kind of a slower process. Amputation or delivering a baby. That's where the mass can change drastically. The weight, though, if you would go somewhere where there's different gravity, bam, your weight is different, just like that, right? As soon as you are on that new planet, and again, I get that that's hypothetical, but if gravity changes, your weight responds instantly because your weight is basically tied or connected to the pull of gravity. So if gravity changes, then your weight changes. And the way, again, to remember that is the weight has G and gravity has G. Okay? There's something else. We'll leave it at that for now. Oh, I know. So using the words inappropriately or incorrectly, I guess. So for, let's say, like wrestling, really, you say you're going to a weigh-in. Well, not really. Like if you're going to check your weight, it should be a mass in. You're really checking your mass. How much matter has made you up? Did you make the weight class guidelines, whatever it may be, right? So we say it wrong. We use weight for almost everything. When really we're not saying, hey, I'm checking. You guys need to stop. This is your final warning, or else I will find you new seats, okay? So it's a matter of like, hey, is the gravity different here in this room, and then when you go in the locker room and do your weigh-in, did the gravity change? No. You're actually trying to check your body's mass. So really you should say, hey, I have to go to a mass in tonight. Ooh, right? Weight Watchers, right? The diet program really should be like mass watchers. We don't care what the gravity is that's pulling on me. I care about what is making me up, right? So again, we use those words incorrectly a lot. We all know what we mean by it, but technically, we're wrong. But again, both of these words have G's in them. So weight is affected by gravity. Mass is just how much matter something is made of. All right, so an object is going to have the same mass when it's on the moon as it does when it's on Earth because the amount of matter hasn't changed, right? That astronaut is still the same astronaut as when they left the Earth as when they're walking on the moon's surface. Now, unless that astronaut has gone through an amputation in space or has delivered a baby, which to my knowledge that has never happened, the mass is going to stay the same. So for all intensive purposes, we could say mass will stay the same. Okay. Now, weight will definitely be different because we have very different gravities on the Earth as we do on the Moon. The Moon is about 1/6 of Earth's gravity. And because of that, the weight will also be about 1/6. So if I go to the Moon and I'm like, woohoo, like I lost all kinds of weight, I'm so skinny now, or maybe you're trying to beef up and gain weight, and you go to, let's say, Saturn, which has a stronger gravitational pull than the Earth, you're like, oh yeah, I really bulked up. Nope, it's still just you, right? It's just because gravity is different. It has nothing to do with what's making you up, okay? And so here's the rule. Anytime you have a different amount of gravity, an object with the same amount of mass will have a different weight. Weight is affected by gravity. So whatever gravity does, that's what it's going to do to weight. So if gravity increases, weight increases. If gravity decreases, then weight decreases. And through all of it, mass is the steady one, right?
Man, my time.
Right. So really the only places that there would be different amounts of gravity is if there might be like some kind of a simulation. NASA does have simulations where it's like a zero gravity environment or close to zero, but really we're talking about planets here. So here's the Earth, the Moon, Jupiter, and the Sun. So a person's mass is 63.5 kilograms, and really a kilogram is every pound is 2.2 kilograms. So, excuse me, I said that backwards. For every kilogram, it's 2.2 pounds. So really this person would be like right around like 130 some pounds, maybe. So 63.5 kilograms has a weight of 623 newtons, right? This mass is still 63.5 kilograms, still 63.5 kilograms, and still 63.5 kilograms. Now look at the weights though. On Earth, if it's 623, going to the Moon, woohoo, 1/6, so it's only about 100 newtons. Jupiter has a much stronger pull, and you can see that by this arrow, right, trying to show that it's bigger than Earth's pull. The weight would be about 1,582 newtons, and then the Sun is our biggest, right? All of our planets actually revolve around the Sun because it is the most massive in our solar system, and 17,418 newtons. So changing locations, and again, this is hypothetical, right? We can't actually go to the Sun. We haven't actually been to Jupiter. I've been to the Moon. But this is letting us know. So you go from basically a 130 to 140 pound person to 3,900 pound person. Again, they wouldn't look physically any different. Look at my little stick person. Still looks the exact same at every location. Hasn't gotten skinnier, hasn't gotten bigger. Still is the same mass-wise. Okay. Okay, and so here we have two astronauts, one on the Earth and one on the Moon. So where will the astronaut have the most weight? What's your guess? What do you think, Macy? Earth, for sure, right? Because the Earth is more massive, meaning it has a larger gravitational force, meaning it has a larger gravitational pull on that person, making that person's weight greater. So then where is this person's mass going to be greatest? Allie's like, what is she doing here?
Oh, I know.
Shelby?
On the Earth.
On the Earth? Who thinks Earth?
It's.
Tucker, what do you
What
think?
do you think on me?
On both?
Oh, you said mass, so I
I
was
did say
saying.
mass.
I
Good.
thought you said weight.
And I can see Abby's face. She's like, is she looking us? Like, this is silly. This is a silly question. And then I saw a light bulb go off in Tucker. Like, oh, wait a minute. Yeah, mass, they're going to be the same. I don't see like an astronaut like that looks like it was pregnant and then not pregnant. And I don't see any amputations. So our two kind of exclusions for mass changing don't look like they're in effect here. So that mass, no matter where that person is going to have the same mass. So they have to be equal. All right, let's go.
Yeah, one more.
Let's do this. Let's go back to, go ahead and put your notes away. We're gonna go to a video and then hopefully we'll have time for the song.
I don't know, since you get